Right, so here we've got a hiker walking up a hill, backpack on. We don't know the weight of this backpack, but we're going to work it out, okay? Now you can see the hiker is leaning forward slightly to stop themselves from being tipped over by this presumably fairly heavy backpack. Now, there's a lot of things going on here. The first thing is that's the weight of the hiker acting downwards, the weight of the backpack acting downwards, okay? And they're both caused by gravity acting on those masses. And then we've got the friction force acting up the slope. And then we've got the reaction forces. The reaction force is just as the backpack and the person's weight pulls the person downwards, the surface produces a normal reaction force that is always at 90 degrees to the surface, and that reacts on each foot, okay? Right, so there's two things we can say here. Because we know the whole situation here is in equilibrium, we know that the total resultant force has got to be equal to 0, but we also know that the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments. So there's no net resultant force, no net moment. So we can start now thinking about how we're going to work out W. Now, the first thing we're going to think about is the resultant force. And we're just going to consider these forces that are perpendicular to the slope. We're going to ignore friction for a minute. Okay. So the way we're going to do this is we need to think, first of all, the reaction force is perpendicular to the slope, but these two forces are not perpendicular to the slope. So we need to work out the perpendicular components of these two forces to the slope. And the way we can do that is as follows. So if we redraw the slope like this, just to simplify the situation, okay, there's 20. We know that the weight is acting downwards like this. Okay, I'm just going to extend it a little bit. So that's your weight W. And then we can think about that weight as split into two components. So we've got the component perpendicular to the slope and the component parallel to the slope. Okay, now we know this angle here is 90 degrees. We know this angle here is 90 degrees. If you think about this triangle here, that's 20, that's 90, so that makes 110. So this angle here must be 70 because the angles in a triangle have to make 180. Now, if you think about this, you've got the slope, this blue dotted line here, the component of W perpendicular to the slope, is perpendicular to the slope. So we know that that angle there is 90. Equally, the angle between the slope and the dotted line on this side, on the left-hand side, is 90. But we've got 70 of that here, which means that this angle here must be 20. Okay, so that angle there and that angle there are the same. So if we want to work out the component of W that is perpendicular to the slope, we're just going to use trigonometry. This is a right angled triangle. This forms the adjacent, this forms the hypotenuse. So we're going to use cos theta. So if you think about cos of theta is equal to the adjacent over the hypotenuse. So therefore, we're trying to work out the adjacent. It's going to be h cos theta. H is W cos of 20. Okay, so the component of W perpendicular to the slope is W cos 20. Now, if you think about also the component of the person's weight perpendicular to the slope, so this component here of the person's weight, that's just going to be 740 cos 20 for exactly the same reasoning as we went through here. Okay, so that means we can now think about, we've now got two forces perpendicular to the slope acting sort of down to the right, which is 740 cos 20, and this here is W cos 20. And then we've got two forces acting up to the left, which are R. These two forces and these two forces must sum to make 0, okay? And therefore we can write this, 740 cos 20 plus W cos 20 is equal to, so these downward forces are equal to these two forces here, which is 2R, okay? So what all that is saying is the total downward force, so to speak, downward to the right force, is equal to the total upward to the left force, okay? Because these forces are acting in the same line, aren't they? they're acting in the same, along the same line. So no resultant force there, okay? Now, the next thing to think about then is to simplify this a little bit. So if you simplify this, you're going to get, this is going to give you 695. This is going to give you cos 20 here just comes out as 0.940 W, and that equals 2R, okay? So we just simplified that equation a little bit. Okay, so the next thing to think about now is the moment, okay? So we're thinking about moments now. So sum of the clockwise moment equals the sum of the anti-clockwise moment. That's where we're starting off. And then if you come down here, you can see we've got a situation with moments. So we're going to use O as our pivot point. And you'll know from moments that the moment is the force multiplied by the perpendicular distance from the pivot. Now here, we've got an issue. We can either work out the perpendicular distance of this force from the pivot, or we can make this force perpendicular to the surface here that we're considering, or to the object that is pivoting, okay? So we're going to make this perpendicular, and the way we do that, as we already know that this angle here is 20, okay? So we know here that this is equal to 740 cos 20, and if we work out the perpendicular component of W, we know that that's W cos 20. All right, so we've got this force acting, causing a clockwise moment, this force causing an anti-clockwise moment about O, and this force also causing an anti-clockwise moment about O. So clockwise moments, we've got 740 cos 20, that's that one, but multiplied by the distance, which is 0.25, the distance from the pivot. That is equal to 0.40 R, because that multiplied by the distance, that's acting anti-clockwise. This is also acting anti-clockwise, so that's W cos 20, times 0.1, okay? Right, so we can then simplify this. 740 cos 20, okay, is going to give you and multiplied by 0.25. So 740 cos 20 multiplied by 0.25 gives you 174. That equals 0.40 R, plus cos 20 times 0.1 gives you 0.0940, and then multiplied by W. Okay, so we've simplified that. So now we've got two equations. We've got this equation and this equation, and we need to work out W. So we need to make R the subject and then substitute it into this equation here. Okay, so the way we can do that is just, we know that 0.40 R is equal to 174 take away 0.0940 W, okay, so I've just rearranged that equation there to make that. That's supposed to be a W there, sorry, I'll rewrite that. So 0.0940 W. And then we can divide both sides by 0.4, so that's going to give us R equals 435 minus 0.235 W. So all I did there was divide both sides by 0.4. That's supposed to be an R, by the way. And then finally then, we can take this equation here and we can substitute it into that equation there. Okay, so we're going to take this and substitute it into there. All right, so I'll go back to another colour perhaps to do that. Okay, so we know that all of this here can go into that equation there. Okay, so 0.940 W plus 695, so just rearrange, I've just swapped those two around, is equal to 2 times 435 minus 0.235 W. Okay, so that's what we've got. So we need to multiply out this bracket here and take this over the other side. So if you multiply out the bracket, you're going to get 870 minus 0.470W. All right. And then if you collect the terms, so if you take this term over this side, take this term over that side, it's going to simplify to 1.41W equals 175. Okay, so all I've done there is I've just collected the terms on both sides and simplified. And then I've got to just divide both sides by 1.41 now, and that will give us W equals 124 newtons, okay? And I've made that 3 significant figures because I think the data we were using was 3 significant figures earlier, okay? So there you go, that's the answer.